Okay, so we just talked about point number 5, which was other halogenation reactions. Other halogenation reactions, and the key takeaway was that fluorination is very, very exothermic and it's almost explosive. Chlorination is kind of in the middle. Bromination is still exothermic, but very mildly exothermic. Iodination is very, so it's actually endothermic, so it doesn't occur thermodynamically. Alright, so that's what we did on that slide. I'd recommend printing or saving that PDF, integrate it into your notes somehow, either electronically or as a piece of paper you can print out, and that's going to help you. Alright, so we're on to 6. So we're going to call this chlorination of higher alkanes. Chlorination of higher alkanes. What do we mean by a higher alkane? Well, what's the alkane we were just talking about? Methane, right? Methane's a kind of boring alkane. Let's try something bigger, like ethane or propane, right? C2, C3, larger molecules. Okay, all right. So let's think about chlorination of ethane. H3C, CH3. Alright, and let's react it with Cl2, ClCl. And what do you think it's going to make? So the first thing is that is not enough to get the reaction to go. I mean, you'd imagine that if you react ethane and chloroethane, you'd get ethane and chlorine. Ethane and chlorine, you'd get chloroethane, right? H3C, CH2, Cl. And the byproduct is what? HCl. And alright, so the byproduct's not that important, so I wouldn't really worry about that. And I mean, if I ask you to see all the products, you might say, oh yeah, there's some HCl also. But anyway, remember I'm missing something. Mechanistically, it was that you need light or heat. Heat or light to get the reaction to go, because there's a little bit of an energy barrier, and especially for the initiation reaction, the first thing where the Cl2 falls apart, right? Okay, well that's actually not that crazy. We just chlorinated ethane, and that, you know, there's one product. I'm going to call this monochlorination. Monochlorination. What does monochlorination mean? It means we're chlorinating once. We're assuming we're not adding like another chlorine, because you could imagine there's 2 carbons. Maybe we can get an extra chlorine on there. But we're not doing that. We're keeping this simple. Monochlorination of ethane, all right? Okay, so what about propane? So we did ethane, let's do propane. H3C, CH2, CH3. All right, so it's 3 carbons. We're going to react it with chlorine. A heat or light. How many products are there? How many products, like organic monochlorination products are there? So how many products would form how many products would form organic products if propane reacted with chlorine? Unique products, right? So you might ask yourself, well, how many carbons are there? Well, there's 3 carbons, right? So you might say, well, there's 3 products. 3 carbons, 3 products. But this is, but that's wrong. because I said unique, right? So the question here is how many unique products? How many unique products? Okay? How many unique products are there? Well, the reason there's not 3 is because the end carbons are the same, right? Methyl on the left, methyl on the right, they're the same. And so there's only 2 products. One where the end ones get chlorinated, and one where the middle one gets chlorinated, right? So what do the products look like? I'm going to draw them over here, and I'll stack them. I'm going to ignore the HCl also. All right, so we could imagine you might make some Cl, CH2, CH2, CH3, Cl, CH2, CH2, CH3, right? And you might also make one where the middle carbon gets chlorinated. So that would be H3C, CH, chlorine, and CH3, right? All right, so those are the 2 products. I'm going to give them names or letters. I'm going to say A and B. All right, so we have product A and product B, right? All right, so, and of course if you chlorinate the right side carbon, what would that give you? It's the same product as A, right? One more thing we can do is give them IUPAC names, the nomenclature. What's the name of this? 1-chloropropane, right? 1-chloropropane. 1-chloropropane. What's the IUPAC name of the second one? 2-chloropropane. When I say IUPAC, IUPAC is that naming convention, International Union of Pure and Applied Chemistry. They created this whole idea of naming molecules, right? All right, so we got 2 possible products, A and B, right? All right. So this is always a little confusing, but we're going to get through it. All right. What would the like if all of the reactions, you know, with the chlorine, all happened statistically equally, you know, based on equal probability of the different hydrogens reacting equally, right? What would the ratio be of A and B? What would the ratio of A to B be, right? Like, how much would I expect of A and B? And so, the way I'd say that, another way to say that is, what would the probable distribution be? Of A and B, like A to B, right? If all CHs reacted equally. Does that make sense, what I'm asking? What would the probable distribution of A to B be if all of the CHs reacted equally? All right? And the answer would be that A to B is what? You have to announce it through YouTube to me. The answer is, it looks like there's 6 hydrogens on the outside. That would give rise to product A, right? 3 there, 3 there. So it would be 6 to 2, right? Because there's 2 hydrogens that if they were replaced with chlorine, that would give rise to product B, right? So we have 6 that would give rise to A, and 2 that would give rise to B. And of course that means that's the same as 3 to 1. So assuming that all of the hydrogens reacted equally, you would expect a what? A 3 to 1 mixture of A to B, right? You'd expect 3 A's to 1 B. You'd expect that, right? But experimentally, it's not that. And that's weird. The book goes into this, of course. Experimentally, you do this experiment. You actually do this in the laboratory. You get some propane and you react it with Cl2. And experimentally, you do this, and the answer is not 3 to 1. It's actually 43 to 57. That is a little weird. This is what you'd expect, assuming all the H's react equally. But experimentally, it looks like it's not 3 to 1. It's actually 43 to 57. So which one is being produced in larger quantities experimentally? 43 to 57 versus 3 to 1. It looks like there's a lot more of the internal chlorination, right? A lot more internal chlorination. A lot more B, right? And what might, well, there's an explanation for that, of course, that you're getting a lot more of B. I'll jump ahead a little bit, because when you think about the mechanism, right, and you initiate, make some Cl dot, and then the propagation, what's propagation? It's like you have Cl dot, and then it'll pull off H's, right? Okay, so if we pull off the end H's, what kind of radicals do you get? Primary, secondary, or tertiary? Right? If you pull off an H from there and you make a CH2 dot, right? A CH2 dot, is that primary, secondary, or tertiary? The answer is it's primary, right? It's primary. If you pull off an end carbon, it's primary. What if you pull off the middle one? That's secondary. If you have a radical there, imagine you have a dot there, and there's carbons on both sides. That would be a secondary radical. And then what do we know about primary radicals versus secondary radicals? We know that secondary is better, more stable, right? Well, that kind of already is the explanation. So, jumping ahead a bit, experimentally, we get a lot more internal chlorination. We get a lot more B. The reason is because you go through a more stable secondary radical, All right? Cool. So that's kind of what's going on here. So we know that secondary radical that would be formed there is more stable than a primary radical. Okay, so we can actually go a step further. Alright, so we're going to go a step further now, and we're going to calculate how much more is the secondary chlorination preferred versus primary. All right. Now the calculation is a little. It looks a little scary. It's not. It's not that scary. Don't worry about it. If you get stuck on the calculation, don't worry, and you're not going to be asked to do the calculation. But we will need the result of it. So what we're going to determine is we're going to quantify the amount of secondary chlorination versus primary chlorination. We're going to quantify the amount of secondary versus primary. So the calculation is this. So we're going to do a little bit of math. It's not that bad. It's the experimental yield from secondary chlorination divided by the number of secondary positions. Okay? So, and then on the bottom we're going to do the experimental yield from primary chlorination divided by the number of primary positions. All right? When you do all this, so experimental yield was like what we got from the experiment that we saw above, and then the number of positions is just the number of hydrogen atoms, right? So for secondary, experimental yield and the number of positions. Let's look at it. So secondary is going to be that kind of the middle position, right? So what's the experimental yield for secondary? It was 57. So it's 57 divided by the number of secondary positions. How many secondary H's are there on that secondary carbon? There's 2, right? So it's 57 divided by 2. Okay, and the experimental yield from primary chlorination, what was that? That was 43. How many primary positions are there, like H's, that would give you the primary product? How many H's are there? 3 plus 3 is 6. Okay, do all the math and you get 4, roughly 4. Okay, so 4. And so 4 is going to be a kind of a magic number, that, like a real magic number that we're going to use in these problems in a bit. What does 4 mean? 4 in this case means, therefore, I don't know if everybody uses this in math or whatever to say therefore, secondary positions are some amount of times more reactive than primary positions in chlorination. So it's specifically for chlorination. Okay, so it's secondary positions are some amount of times more reactive than primary. What's this amount of times? It's 4. So it's 4 times. Secondary positions are 4 times more reactive than primary positions. And it's, you know, in a nutshell, it's due to the radical stability of the primary site. The, you know, when the primary, sorry, the secondary site is a little more stable when you rip off that H and you get a secondary radical. All right, and its secondary positions are 4 times more reactive. Cool. Let's do another one. Another example. So let's do, this time it's a slightly different molecule. Whoops. What's the name of that molecule? Looks like it's propane with a methyl on 2. So it's 2-methyl propane. 2-methyl propane. React with Cl2, same thing, light or heat. And how many different products would you expect in this example that you could chlorinate? You know, how many different products are there? Just like you did before, you could envision maybe like chlorinate the methyls, so that's like one product, and you could chlorinate the internal position. So there's like 2 products, right? Let's draw them. Cl, CH2, CH, CH3, CH3. This is a case where I'm not drawing skeletal. I think it's, you know, these really simple molecules, it's almost easier to not draw skeletal. So I'm drawing each of the H's out. All right, and so of course you could chlorinate the outside carbons, and we'll call this A. You could also chlorinate the inside carbon. What do you think? What letter should we give that? Maybe we'll give it B. Alright, so we make products A and B. Alright, we're going to do the same exact thing we just did. Alright, so if we, what's the expected distribution? By chance, we'll say, by chance. So if there's no preference for the outside carbons or inside carbon, what would be the expected distribution? Well, it looks like there's 9 hydrogens on the outside and 1 in the middle, right? So it's 9. 9, if we do A to B, between 9 H's on the outside to 1 H in the middle, right? Alright, but really, observed is what? So the actual observed, the really observed one is 64 to 36. 64 to 36. So just kind of like before, in the last example, in the last, the one we just did, we showed that primary versus secondary, secondary is 4 times more likely to react. Now with this one, it's not primary versus secondary. It's actually, the H that gives rise to product B is not secondary. How many things are on that carbon? There's 3, so it's tertiary, right? So this is a little different. It's actually tertiary. And we also know that tertiary radicals are a little more stable. They're the most stable, right? Tertiary radicals, super stable. Okay, so it looks like, just like kind of in the last example, there's more of product B than you might expect if it was just by chance. 9 to 1 is not the same as 64 to 36. So the reasoning, the why there, is tertiary radical is more stable than a primary radical. That makes sense. We know that. We know that tertiary radicals are more stable than primary radicals. All right? We do the same quantification. Quantify. It's the yield of tertiary chlorination divided by the number of tertiary positions divided by the yield of primary chlorination and then that's divided by the number of primary positions. Oh, sorry, I'm not sure if you saw that all, but yeah. when I'm recording, I don't necessarily see what it's recording, but here and there I do. All right, so it's the same exact formula. Yield of tertiary divided by the number of tertiary positions divided by, on the bottom, so this whole top term is divided by the bottom term, which is the yield of primary chlorination, which is divided by the number of primary positions. Okay, what is the yield of tertiary chlorination? Yield of tertiary chlorination is this 36. And how many tertiary positions are there? How many tertiary positions are there? There's 1. 36 divided by 1. And then what's the yield of primary chlorination? It is 64. 64. And what's the number of hydrogens, primary positions, that would give rise to that primary product? Well, how many H's are there? 3 plus 3 plus 3 is 9. Do the math, and it's 5. So you do the math, and it's 5. And the conclusion is that a tertiary position is 5 times more reactive than primary. A tertiary position is 5 times more reactive than primary. That's the conclusion, right? So it's like secondary, we did primary, secondary, and tertiary. Secondary position, so this is tertiary, but we just did the other one on the last page. Secondary positions are 4 times. Tertiary positions are 5 times. It's just a little more reactive, and why is it more reactive? Something about the radical stability. Tertiary radicals are a little more stable, right? Okay, so how do we summarize all those little experiments we just did? We say overall, the reactivity difference is 1 to 4 to 5 for primary to secondary to tertiary. Okay? Primary to secondary to tertiary. Alright? And this is specifically for chlorination. So we're going to see when we do bromination and fluorination that the ratios are different. That's just foreshadowing a little bit, right? So the reactivity differences are a little bit different for bromination and fluorination. Different for F2 and Br2. Also, just a little bit of foreshadowing. Which one of these is crazy explosive? The fluorine one, right? And this is called selectivity. It's like, yeah, you know, tertiary is kind of selective. There's an extra probability that tertiary is going to react, and you know, secondary is in the middle. Primary is kind of less selective. When you have a reaction like fluorination, which is explosive, the selectivity goes away. And what we're going to see later is that fluorine gives you almost a 1 to 1 to 1. There's going to be a little bit of preference for secondary and tertiary, but not as much as this. All right. Okay, so let's do a book problem. Book problem. I think this is. I think it's problem 3.8. I think it's problem 3.8. That should be 3.8 in the definitely the 6th and I think 7th edition. You should try this book problem yourself, but let's do it together. So basically it's asking to estimate the product distribution of monochlorinated products. Estimate the product distribution of monochlorinated products for this reaction. So we're going to react H3C CO there we go. Cl2, light or heat. And I'm drawing my chlorine over the arrow here. It's not a big deal. Sometimes we do that. Sometimes we move the chlorine to the left. It's kind of arbitrary. Alright, so the first really important thing here to do this, and we really got to be diligent about doing this correctly, because you're going to do problems like this in the quiz. The first thing we need to do is determine the number of, well, before we do the estimate the product distribution of monochlorinated products, we need to figure out what the possible products are. What the possible products are, right? And so, and what we need to do is think about, how many unique carbons are there? That's a good way to begin this. How many unique carbons are there? Because, like, looks like we have these guys, we have the central CH, we have a CH2, we have a CH3. How many unique carbons are there? How many carbons total are there? Well, there's 1, 2, 3, 4, 5. There's 5 carbons total. So what are the unique monochlorinated products? Okay, now these two CH3s look kind of the same. There's some symmetry there. So we can imagine that you can chlorinate these guys, right? And that would give you one unique product. So I'm going to draw these in skeletal format. And I'm going to call that A. Alright? And what's the next unique monochlorinated product? I like to just be systematic, and I'll go kind of left to right here. So we address these 6 hydrogens, and it looks like this is the next carbon left to right. So maybe you could chlorinate that position, right? Chlorinate that central position. So alright, so that's maybe product B. And then you could imagine maybe we could chlorinate the CH2, that position, right? Alright, and then what about the end position? So that'd be product D, right? Okay, so these are the 4 unique chlorination products, and again, it's nice to be systematic about this, and just kind of start at one side and go to the other. And if there's symmetry, like these two CH3s are symmetrical, then they're going to give rise to a single product. But these are 4 unique products, and they also have 4 unique IUPAC names. You should be able to name all of these, right? It looks like it's 1-chloro-2-methylbutane. 1-chloro-2-methylbutane. This is 2-chloro-2-methylbutane. I think this is 2-chloro-3-methylbutane. And this is 3-methylbutane. 1-chloro-3-methylbutane. So writing the names out will also help you here. One more trick is that once I know how many unique hydrogens there are, because there's like 1, 2, there's like these guys are 1, 2, 3, 4. What I like to do, a really quick way to do this, and I'm going to get a different piece of paper real quick. All right, so we know the structure. What I do is I'll just draw 4 copies of the starting material essentially. And then I'm like, just start with the skeletal. And then I'm like, okay, well, we have a chlorine there, we have a chlorine there, we have a chlorine there, we have a chlorine there. So if you just draw 4 copies of your starting material in skeletal format, then you can just draw quickly the different chlorine substitution patterns, all right? Anyway, so we got our A, B, and C, and D. Cool. So now what? How do we do this? It's a pretty easy process. It's a calculation, and you will do this calculation on a quiz. Okay. All right. So what I do is I write A, B, C, D. Start with that. Write A, B, C, D. Because you have 4 products. Now we just have to figure out the estimated yield of those 4 things. All right. The way to do this now for A, B, C, and D is we're gonna for A first. The question is, how many hydrogens on the starting material could be replaced with chlorine to give you product A? That's the question. How many hydrogens in the starting material could be replaced with chlorine to give you product A? All right, think about that a little bit. How many hydrogens could be replaced with chlorine in the starting material to give you product A? Well, it looks like there's 2 CH3s and they're identical, so 3 plus 3 is 6. So that's what we write here, 6. All right. Let's ignore what's to the right of the X first. For product B, how many hydrogens would give rise to product B? Well, there's only 1, right? So it's 1. For C, how many hydrogens could be replaced with chlorine in the starting material to give you product C. So what I usually do is I kind of look at product C and I move my pen around there. I'm like, well, that's the carbon here. What's the carbon over there? And how many hydrogens are there? Ah, there's 2. That's right, 2. And for D, how many hydrogens in the starting material could be replaced with chlorine to give you product D? So I look there, I'm like, well, that's the carbon, and let's go look here, and how many hydrogens are there? There's 3. Okay? So that's the first thing. We're almost done. This is not a hard problem. It's always a little weird at first. The next thing we need to do is write the experimental yield, or the experimental probability, you know, that we figured out. What was it? It was 145, right? Primary, secondary, tertiary. So now for 6, we figure out, you know, these carbons, are they primary or secondary or tertiary? Those 2 CH3s are, they're primary, right? And what's the number for primary? Is it 1, 4, or 5? It's 1, because they're primary, right? The rule is 1, 4, 5. And then for the tertiary, is a tertiary, so what's the likelihood of a tertiary? 1, 4, or 5? Well, it's 5, right? Okay. And then for secondary, what was the rule for secondary? 1, 4, or 5? It's 4. And then for primary, this is another primary, right? It's like you have the left primaries and the right primary. It's 1, 4, or 5. That's 1. Okay. Now you just do math. This is 6. This is 5. This is 8. And this is 3. 6, 8, 5. 6, 5, 8, 3, right? Now, all we do is we add them up. Okay? What do you add them up, you get 22. And the very last thing is now for A, B, C, and D, you just do the percent of, you know, 6 divided by 22, the percent, 5 divided by 22, 8 divided by 22, and 3 divided by 22. We get 27%. We get 23%. We get 36%. And we get 14%. So here's the winner. Which of these products will be formed in the most quantity? Which percent's the highest? It is C. The winner is C, right? Okay, so that's a cool problem. And it's going to be cooler when we do bromination and fluorination because the selectivity changes a little bit. It's not going to be 145. Anyway, so this is a cool problem. Try to do this problem, and we'll you know, once we have bromination and fluorination down, it'll even be cooler. It'll even be cooler because those give you a very difference in selectivity. All right. All right. So we talked about chlorination of higher alkanes, and let's get into what I promised earlier, which is the selectivity of fluorination versus bromination. And we already said fluorination, being a very explosive reaction, is actually not selective. So, and we'll see that. All right. Cool. So let's show an example. First, fluorination. Let's do H3C, CH, CH3, CH3, and let's react it with F2, light or heat or light. And what are the products? How many unique products do you get? Monofluorination products. Well, you have basically two kinds of carbon, and so you can imagine what the two products are going to be. Fluorine's on the outside, fluorine's on the inside. It's just like chlorine, we just did this. There's two products, and using my little strategy that we just showed you, I would just draw two skeletal structures that contain the skeleton, right? And I'm gonna just assume maybe we have F on the outside and F on the inside. So we have A and B, right? You might expect a little bit more of the middle fluorination due to the tertiary radical intermediacy, right? Because this goes through a tertiary radical. Anyway, expected by chance. What's the expected by chance? Again, it's essentially just the number of hydrogens in the outside versus the number of hydrogens in the inside. So if there's no selectivity at all, it would be 9 to 1. All right, and if observed experimentally, is almost that, 86 to 14. So that's a pretty huge deviation from what we just saw with chlorination. Chlorination had a pretty big preference for internal, right? Due to the chloride, the tertiary radical being more stable. There's a little bit of that with fluorine, but not very much, right? So we'll say it's mostly non-selective. Mostly non-selective, right? Fluorination is a kind of a non-selective reaction, right? What about bromine versus bromine? So bromine, let's do the same exact experiment. So I'm just going to recopy what I did up top. Alright, and what are the products? Just draw two skeletal structures. Without bromine, and then you add the bromine. Bromine there, and bromine there. Alright, let's give them labels, A and B. Expected by chance. Is the same as above, 9 to 1. Because you got 9 hydrogens on the outside and 1 in the middle. Observed experimentally. Is, I always have to double check this because this is crazy. Observed experimentally, because above is like basically not selective at all. For observed experimentally here, it's less than 1 to 99, which is insane, right? It's a very profound selectivity, right? You're getting tons and tons and tons of internal bromination. Somehow, what's the explanation that we give? What's the explanation, for why we'd even get any internal selectivity? It's something about the tertiary radical. We know tertiary radicals are really good, right? It's not a big deal with fluorination because it's so exothermic and kind of explosive. But with bromination, you get tons, 99 to 1 roughly, of the internal, the tertiary site bromination. So there's a lot of selectivity. This is extremely selective. Extremely selective. Okay, so I just want to, we're basically done. All I want to do is just like I showed you 1, 4, and 5 for chlorination. I'm just going to show what those numbers are for bromination and fluorination, and then we'll continue next time. So assuming we normalize primary versus secondary versus tertiary selectivity. These are the numbers. And these are magic numbers, but you know, I would give you these on quizzes and stuff. So we're going to consider chlorine versus bromine versus fluorine in this order. And we already did chlorine, right? So primary versus secondary versus tertiary. All right. What were the numbers for chlorine for primary versus secondary versus tertiary? They were 1 to 4 to 5, and we calculated these, right? I'm not going to calculate them for bromine. I'm just going to tell you them. It's 1 to 80, so that's, you know, very selective, much more selective than chlorine, to 1700. So bromination is very, very, very selective for either secondary or tertiary compared to chlorination. And then for fluorine, which is not fairly non-selective, it's 1 to 1.2 to 1.4. Okay, cool. All right. So there's some problems, and we'll do these problems next time. I think we're going to get to, well, we'll probably do them a little bit in the lecture, but you can just like do the same kind of thing where it's like, let's do this. I'm not going to do it for you, I'm just going to draw it out. You know, if you have that, you brominate, you get 4 products. Br, 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 and Br, right? You should be able to calculate these, and most likely one of these is going to be very, very selective, right? I'll just tell you, I mean, obviously tertiary selectivity is really crazy with bromine. So you do the math and you'll get this. We'll do the math next time, or you can try it yourself, alright? Cool, that's it. If you have questions, office hours, email, etc. Alright, hope you're doing well. Oh yeah, one more thing. Don't stop the video. I'm going to give a magic word for this concept of selective halogenation. And it's actually topic 7, which we're on. We're on selective halogenation, bromination, fluorination, and determining these product mixtures. So if I ask you for the magic word, and I probably will, I'll say, what's the magic word? The magic word is pickle. So sneak that in your notes, and you can put that in, you know, topic 7, section 7 of this. The magic word is pickle, because we all like pickles. I like pickles. You might like pickles. And so I'm going to ask you these magic words. We have 5 total now in this chapter. We had 4 for the mechanism, and then the 5th one is pickle, which just kind of refers to this general, you know, if you're forming a mixture of products, the magic word is pickle. All right, see ya.